So, for the audience, this presentation will be under a G rating. There will be no profanity from me.
Not from this group.
Yeah, I can't speak for my co-speaker. But anyway, some of you will get that joke, and I'll just leave that there. Though this may be a horror movie for some of you when you hear what we're intending, or very exciting, hopefully. It will be interesting. So like any good talk, we have some sections. We have what, why, who, and how. And hopefully by the end of them, you'll get some sense of what we're trying to do around computational storage using NVM Express, and trying to convey why this is important, who's working on it, and how we think we might be able to move forward collectively as a group, as a team, through standards and consortia to make NVMe even more successful than it already has been. What? So I have to give Michael Cornwell $1 every time I put up this slide, which is kind of unfair because he's a GM and partner at Microsoft Azure, and I'm doing a startup. But anyway, Michael did this slide last year. He's done it a couple of times, and I have as well. NVMe is a transport. It's a mechanism by which operating systems and devices can talk to each other. It's a mechanism by which hosts can manage devices at scale. It's a mechanism by which we can get information or instructions or commands from point A to point B, and that makes it much, much more than just an interface between an operating system and a solid-state drive. And that really is something that the industry has latched onto. It's certainly something that our customers are very much in agreement with, and I think it's something that's going to drive the industry forward in some pretty interesting ways over the next few years. Another way of saying that is NVMe is the one driver to rule them all. So this is the ring from Lord of the Rings, and I kind of hacked that, so one driver to rule them all. So NVMe has been incredibly successful as a storage protocol. I don't know who was at OCP last week. I think a lot of us were. Mellanox announced something called Snap, which is Sexy NVMe Accelerator Platform, I think. If it's not, it should be. There's also things like AWS Nitro. So we're starting to see smart NICs appear that have an NVMe interface to the host. So that's not NVMe over Fabrics. That's plug in a NIC, and it doesn't say it's a NIC to the OS. It says, I'm an NVMe device. So we now have this ability to do networking at an NVMe endpoint, and the smart NIC hides some of the networking stack from the host. The host benefits from offload. Annapurna was bought for exactly this kind of idea, right? So NAFA always tells me I'm just catching up with stuff he did a few years ago. So the question then becomes, why not extend NVMe to computation and make NVMe the one driver to rule them all? And that's what we're going to talk about a little bit going forward. But before we do that, we should really talk about some definitions. SNIA, in the form of the Computational Storage Technical Working Group, has been very busy over the last 3 or 4 months, starting to lay some groundwork around where we're going to go with computational storage and NVMe computational storage. So we've been working on some product definitions. We have things like computational storage drives, which are basically compute added to an SSD. We have something like computational storage processors, which is a computational element without local storage. So this is the kind of product that my startup is working on, where we use the NVMe computation, and we assume we are very, very close to NVMe drives, but we're not necessarily an NVMe drive ourselves. And then there's products like computational storage arrays, which take these smaller building blocks, put them together, and present a larger system that has both storage capabilities and processing computational capabilities, all in one package. So that's kind of the what. Let's talk a little about the why. So why NVMe? So this is a slide that we had at SDC last year. So if I look at computation and I think to myself, what do I need from a driver? What do I need from a protocol that I need to talk to computation devices? Some things come to mind. I need low latency. I need high throughput. Ideally, I have a lightweight protocol mechanism, so something that's got good cache line awareness, something that scales well with NUMA nodes, something that kind of lines up with IRQ affinity. I certainly want to be multi-core aware, right? These large servers and data centers now have tens, if not hundreds of cores. So having something that doesn't scale well across cores is not a good idea. So don't have central locks, right? Central locks are bad when you have 100 cores fighting for a lock. Doesn't work, right? So I want to have management at scale. Very, very important. I was at a large hyperscaler last week. They went, we love all these accelerator startups, but they never think about management. If I buy one accelerator, I need to buy 100,000. How do I manage that? In fact, one of the AI companies came to this large hyperscaler and said, we got an awesome, awesome, awesome device. The data plane was awesome. They hadn't even thought about management. And this hyperscaler was like, I can't consume you. How could I possibly consume you? Right? Even if you were the best AI accelerator on the planet, if I can't manage you at tens or hundreds of thousands of nodes, I cannot deploy you. Right? So this is sort of the thing that NVMe instantly solves with the work Peter and the team in the MI group are doing, because this is just another NVMe device in a system that already has tens, if not hundreds, if not thousands, if not tens of thousands of NVMe devices already. QoS awareness is really, really important. So obviously, what does NVMe give me? It gives me all these things, right? So the real question is, why not NVMe for my accelerators?
So back when I started out, we weren't worried about gigabytes per terabytes. We were worried about kilobytes per megabyte to manage flash. Today's data sets behind NVMe are huge. It's kind of like fishing. When you go fishing and you're trying to find a particular fish, it's pretty tough these days. You go out, you catch one, you look at it, is it the right one? No, it is not. What you're looking for is some intelligence, some computational capability inside of that storage to deliver that one fish to you. In this case, the orange fish. And that's really the basis of a lot of what computational storage is to minimize that work, to be more intelligent about how you find the information that you're looking for. And that's very important when you're talking about these very large data centers with their very large data sets and all the dories that are out there when you're trying to find that one Nemo.
So just a couple of use cases that we find have gained some traction in the market. This is not, we're trying not to be very vendor specific here, but based on conversations we're having with customers, these are the kinds of things people are interested in terms of deployment. So where, some companies are building NVMe systems, well, many companies are building NVMe-based systems already. They need computational services inside those systems. Those could be computational services that are to manage the data that are on these drives, or they could, like Richard was saying, be services to act on the data that's already on those drives. So some people are deploying things like computational storage processors. These are NVMe devices that do computation but not storage, and they're actually living right down with the drive. So if you look at this diagram over here, we have a mix of standard NVMe SSDs, and we're adding NVMe computational storage processors, or CSPs, to this. And then we're basically writing software on the central processing unit to basically allow data to move between the drives and the CSP, and for the CSP to perform services on that data. And this could be functions that are storage related, like compression or RAID. They could be services that are analytical in nature, like artificial intelligence inference or pattern recognition. But the key thing is the interface by which you go through to program those CSPs is NVMe. And the management plane is the same as the SSDs. This makes this kind of model very, very consumable. And I think that's one thing we have to make very clear as we go forward. My vision, our vision for how we deploy this is consumability for the end user. I want to make our customers and our customers' customers almost not even aware that they're consuming this stuff. If we do our job properly, it's literally plug these things into the system. They get recognized through the NVMe driver stack. If the admin settings are correct, they start getting consumed by applications. And I'll show you a little later in the software stack how applications can take advantage of that. We can also do things like new versions of data movement. Recently, Eideticom upstreamed a new Linux framework called peer-to-peer DMAs. This allows devices to do DMAs directly between each other, still under operating system control. This is now available in the Linux kernel, the upstream version. Anyone who has PCIe devices can participate in this framework. And I encourage you to go take a look at that, because that's a very interesting way of moving data in this computational storage paradigm. NVMe devices already support this paradigm through things like controller memory buffers and persistent memory regions. One of the things I didn't even mention yet in terms of the benefits of going with NVMe is disaggregation of computational storage services. So NVMe over Fabrics allows me to take a namespace from an NVMe controller and put it anywhere I like in the universe over one of the transports that we've defined or standardized around. So with Rocky and Fiber Channel, getting all the way across the universe was challenging. With TCP/IP, it's trivial, right? The latency might suck, but you can do it. And now I can take namespaces that are computational in nature and move them from an array, a disaggregated rack, to the compute nodes that need them over things like Rocky, Fiber Channel, TCP/IP. So now I can, as well as getting my disaggregated storage to work for me in a kind of composable way, I can get my computational services to do the same. And we can construct some very interesting disaggregated resources doing that. So again, NVMe kind of gives that almost to us for free, because that work is already done and we can tie into that. Trying to do something like this for accelerators without leveraging NVMe would be very challenging, and to be honest, would require doing a lot of the work that NVMe has already done. So this kind of makes sense, and it's another benefit of aligning with NVMe.
So if you take that networking aspect to it to the next level, when you start talking about clusters, one example that we've done at our company is actually done a Hadoop cluster and pushed the name node directly down into the storage, virtually eliminating a lot of the I/O. This is all enabled through computational storage capabilities, but it really does require some standards around it to drive it home. In this example, actually, we're showing a benefit in reducing the I/O. We're running a TerraSort on a 16 CPU or 16 core CPU. Replaced it with a 8 CPU or 8 core CPU and 8 of our computational storage enabled SSDs, saw an increase in performance. That allows you to then use those CPUs for other functions to increase the compute capability of the host node or to reduce those altogether. Other examples that we're looking at and hoping to enable in the future is through network offloading. Monitoring information is becoming more and more tedious, more and more cumbersome. A lot of the expense there is in the memory, and you end up having to develop these huge buffers to store the information and that you're going to process. A potential use case would be to extend those buffers into the NVMe space, using the NVMe storage to both store and pre-process some of that information, resulting in less I/O, less energy.
So moving on to the next section, let's talk about who. So just prior to FMS last year, a couple of us got together and went, computational storage is really quite interesting. We were all startups in the space. Let's have a little birds of a feather and see if anybody gets interested in joining us and try to put some standards around this. The only time Lance would give me is 7 a.m. in the morning. Thanks, Lance.
That's Lance.
So we put out the kind of it was even a last minute thing. We said, if you're at FMS next week, 7 a.m., come to this room. We'll have a bit of a buff. We had 30-something people. The room was filled. And we came out of that room unanimously agreeing that we should go form a technical working group within SNIA and go start digging into that. Since that time, the twig has actually formed. We have blessings from the technical committee there. We're now at 32 companies. This is from OCP last week. We may even be above 32, and we have over 100 signed up members. I would ask, if anyone in this room does not see their company logo on this slide, can you raise your hand? Great.
Come to us afterwards.
Come to us. Come see me in the bar. I will buy you beer and try to get you involved. So how is this going to happen? How do we make this work? I drew a little software stack slide, and this for me is, I am a hardware, but I'm also a software guy. I've even contributed code to the Linux kernel, believe it or not. But, the thing that haunts me is we go build something that the end users, which are, in my opinion, the large cloud vendors, the hyperscalers, the HPC people, cannot consume. So my worst fear is a bunch of vendor people in a room coming up with stuff that nobody wants. And I think we talked about that a little earlier in the kind of the validation and features phase. So it's about make it consumable, make it consumable, make it consumable. People have to be able to consume this. So the way that we kind of see this happening is we work within the NVMe community to define identification services, to define APIs, to define any extensions to management interface. And we basically use the inbox NVMe driver in whatever operating system our customers want to deploy in, and we will update that driver as we go along to support this concept of computation. Right? And maybe it's computational namespaces, maybe it's something else. We don't know yet. That's all TBD. But the idea is that it lives within this NVMe framework. Typically, what we have then in terms of between the applications and the operating system is a user space library. This is pretty common. We do it all the time, user space libraries. But now, rather than having a whole bunch of different user space libraries for different pieces of hardware, we can, as a community, collaborate on a free and open source user space library that works for everybody's computational storage devices. I will give you an example. Linus cut 5.1 RC1 on Sunday. And in that Linux kernel release was Habana Labs' first PCIe driver for their new AI inference engine. Anyone want to guess how many lines of code that driver was? Less than 100? You can put your hands up. More than 100? It's roughly 20,000 lines of code. Right? So to enable a new PCIe device that does AI inference took 20,000 lines of code, and that's just the operating system. There will also be a user space library. There will also have to be a binding into TensorFlow, PyTorch, Caffe, anything else you want to imagine. And that's one PCIe AI company. We have 50 of these guys coming. Right? The kernel bloat alone is outrageous. The amount of overlap between this code is outrageous. And back to the consumability point, if a large hyperscaler wants to compare A versus B versus C, they won't even start that work because they can't afford the software time lost by putting their really expensive software people on trying to make this all work in their kernel. Right? So at least Habana Labs upstreamed their driver, right? So it's in the upstream kernel, but it's a lot of code. If we did instead went to all the AI people and said, use NVMe as the interface, we could have no extra lines of code. We'd use the NVMe driver, and we could have one user space library for everybody. And this, I think, based on what I'm hearing when I talk to the large cloud companies, is what they want. It's not what I want. I just want to sell product. But I've got to build what people want to consume. Consumption, consumption, consumption. So, where do we think we need to go from a standards point of view? Computational namespaces have already been mentioned today. I think Amber had that mentioned in one of her slides. So this is one way we could go. This is not set in stone. There's a call to arms slide coming later. But this is one way we could go. We could have computational namespaces, the same way we will have things like key value namespaces, potentially zone namespaces, and of course the traditional LBA namespaces. Every namespace could be managed slightly differently by the operating system, and those namespaces could all have their own identify commands. We could identify what kind of accelerator we are. Are we a compression engine? Are we a dedupe engine? Are we an ARM core that can run Docker images? Are we something else?
We have parameters we can do too.
Yeah, exactly. How do you parameterize this, right? So we're already looking at things like fixed purpose computation. So if something does one thing but does it very well, like a compression engine, that's very different to how you might manage something like a general purpose computation, which is more like the ARM cores that are available in Richard's product. And we can work to define all of those. And then computation over fabrics. Basically, we want to get to the point where user space does not care or even know if that computational storage device is local, PCIe attached, or remote, fabrics attached. And we can definitely get there.
So within the technical working group, we've identified many paths to creating a computational storage device. These are illustrations of those paths, which include an FPGA in front of multiple SSD controllers with the non-volatile storage behind them, an FPGA that's tied tightly to an SSD, giving you computational capability. There are FPGA-only solutions that give you options as far as how you want to manage it. It could be a host-managed FTL or something that's more traditional inside the drive. And then there are single ASIC solutions which port a computational capability internal to the ASIC, so it's a fully integrated SSD with computational capability integrated inside. And one path that we've chosen at our company for how we're going to do that integrated solution would be to be an SSD at the core. So basically, no impact on host reads or writes, uses a standard NVMe driver, and it uses all the standard protocols, but then there's more, which has those dedicated compute resources. There's hardware accelerators to do data analytics, and actually the ease of use, which is enabled through containers and file system awareness.
So we'd like to finish with a call to arms. I think there's some interesting things here. I know my, the customers I've been talking to, the ones that are already putting us into production and the ones that we're talking to are very interested in this ease of, it's all, like I said, ease of consumption. And I think other vendors in this space should also be interested in working in this space. It's very important we get it right. We don't want to build something nobody wants. So if this sounds interesting, please get involved with the Computational Storage Technical Working Group. I would put out a special appeal if you are an end user, if you are a large-scale consumer of things like accelerators, if you have a lot of good software people, please come to us. Even if you don't feel like you want to join the group, please come to us and give us your feedback. Tell us what you like, tell us what you do not like.
Tell us what we missed.
Tell me what we missed, exactly. If you have thoughts on how you as a consumer would consume NVMe computation, let us know. Talk to me or the co-chairs or anyone who's participating. And what's going to happen is as SNIA's work matures, we will start interfacing more and more with the NVMe working group. If you looked at the list of logos on the computational storage twig, there's a lot of NVMe members already in there. There's already overlap. But how we actually interface and how that happens is still TBD. This is early days. This is greenfield. There's a lot of opportunity. And I think there's a lot of potential to add a lot of value, which hopefully equates to a lot of money.
A lot of awesome.
A lot of awesome. So NVMe computation plus computation equals awesome. It's simple math. Thank you very much.
Way to whip them into shape. We have questions, and I have a working mic.
A working mic.
A working mic. In 4 minutes.
All right, I saw Paul's hand first.
So my question is, how do you facilitate people either adapting existing applications or writing new ones that can scale their work across thousands of compute nodes? It's a problem that's been around for decades. Is it something you need to solve, that you need to help solve?
So,
Yes.
yes and no. It depends on the implementation. There are some cases where you can not have to tailor it, but in most cases you will, especially if you're doing a bare metal type of application, you would have to do some level of tailoring. So SDKs, preferably no driver modifications or minimal driver modifications. In the case of NGD, sorry, my voice is not carrying loud enough. In the case of NGD, by using containers, you can run them directly out of box.
Yeah. I mean, I think this diagram kind of shows the path. There's going to have to be a lot of work going into what the interface between kernel space and user space looks like, what the interface between the PCIe and the devices is. But my dream, my end vision is that everything lives inside this free and open source libcs NVMe, which lives on GitHub, and we all as a community contribute to that. And anytime you put a new accelerator into the mix, you have to write a driver for it, and you have to write a binding through a user space library. And what I'm hoping here is that this does it once. And it doesn't matter whether you buy an Intel compression engine or a Broadcom compression engine or an Eideticom or an NGD or a ScaleFlux. The software stack should be identical in all those cases, is where we want to end up.
So we have time for 2 questions. Yeah, this is Satya from VMware. So today, if you see the market, I think majority of the market is homogeneous computing. where there's the x86 platform 90% of the time, 98% of the time, and then we have some peripherals. But now, the market is going towards more and more heterogeneous computing. The GPUs are coming up. There are a lot of accelerator people are talking about. I do see some of the accelerator or distributed computing, so to speak, is what we're talking about here. But whatever we have today itself is challenging to when you talk about typical enterprise customer to manage the life cycle. And I'm just trying to understand when you say consumption, or ease of consumption, what does it mean? Because it's a lot. What we are trying to create is a monster here, in my opinion. I'm sure there's a value in it. I'm just trying to understand what is the path we are taking it to make it easy for customer to consume it. What are the things we are trying to do? Because NVMe drives, you can manage the NVMe dump drives, but there also it's not easy to manage if you're 24 drive in system and the life cycle of those drives, you're doing it at a cluster levels. If you're 32 nodes, it's a very hard problem to solve for end customer to make it very dumb,
I'll give an illustrative example of ease of consumption. So we have a customer who right now, they run a certain service, I won't say what it is, on Xeon cores, and they're talking to a bunch of NVMe drives. They literally plug in our U.2 accelerators and the fans go down. They don't touch they've set up the code, they're using the inbox NVMe driver, they literally hot plug accelerators into the system and the fans go down because the power consumption is dropped and they're getting more work done for less wattage. And that is where I want everybody who consumes computational storage to end up. It literally becomes plug it in, your life gets better, right? In terms of how we get there, it's this community, right?
It's a lot of work.
It's a lot of work.
Yeah.
Don't get us wrong, it's not going to happen tomorrow.
And it's not done yet.
Yeah, but it's done through standards, it's done through ecosystem, it's done through open source code. We need a mic, otherwise.
No, I'm afraid I'm gonna have to cut you off. We're gonna have to
You
avoid
can grab
the
us in the
panel.
bar.
We got two really quick comments from Bill and from Lee, so I promised that I would go there.
So I had a quick question. About 3 slides from the end, you had pictures of your configurations. That one. Is it your intent to imply by this that all communications go through the computational element, or that's just a effect of the picture? And how do you envision 2 different command sets operating at the same time?
The first one is this slide came from Scott, so he just left our model off it because that's what he does.
Yes.
The command set one, Bill, I think we have to discuss in the bar. I'm not going to get into command set in the Q&A, sorry, but we can talk about it on Thursday morning calls for the next little while.
In some cases, yes, some cases, no. So it's a mix.
And so you're asking about, hey, if I see a problem with adoption, and I see from this, I do have a really huge issue with adoption for us, because I didn't see anything in any of the slides about security. So that's the one I want to say. We got to figure out the security problem before we can do it.
Yeah, so I mean, that's a very good point. NVMe has some security features. Yeah. And that's a good point, Lee. And the feedback is duly noted. And
it's actually been brought up a number of times during the TWIG meetings that security is something that will have to be addressed, and hopefully that gets addressed through the standards work.
All right.
Okay.
Thanks everybody.
Thank you very much. Yeah, thank you guys.